Out there, in the silent vastness of space, lies a galaxy unlike any other NGC 262. This cosmic enigma hides secrets so strange, they challenge everything we think we know about the universe. Picture a place where the laws of physics seem to bend, where objects defy explanation, and where every discovery leaves astronomers scratching their heads. Today, we're diving deep into this celestial mystery, uncovering 30 of the most bizarre objects ever found within its swirling arms, from glowing anomalies that pulse with unknown energy to structures so vast they shouldn't exist. These cosmic oddities will make you question reality itself. What makes NGC 262 so special? It's not just another distant galaxy, it's a treasure trove of the unexplained. Some of these objects emit signals that science can't decipher, while others appear to move in ways that defy gravity. There are formations so ancient they might predate the galaxy itself, and others so strange they've been dubbed impossible by the experts who study them. Imagine a cosmic graveyard of shattered stars, or a void where light simply vanishes. These aren't just random quirks of space, they're clues, hinting at forces and phenomena we've yet to comprehend. And that's what makes this journey so thrilling. Every strange object in NGC 262 tells a story, a puzzle waiting to be solved. Some might be remnants of violent cosmic collisions, while others could be signs of something far more extraordinary lurking in the darkness. Could these anomalies point to undiscovered physics or even evidence of civilizations beyond our own? The truth is out there, hidden among these 30 marvels, and together we're going to explore each one. So buckle up, because by the end of this, you'll see the universe in a whole new light. The first marvel we encounter in NGC 262 is something astronomers call the twisted spiral, a cosmic pretzel of starlight that shouldn't exist. Unlike the elegant, symmetrical arms of most spiral galaxies, this one looks like it's been wrung out by invisible hands, its tendrils bent at jagged, unnatural angles. Normally, galaxy arms follow graceful curves, shaped by the gentle dance of rotation and gravity. But here, the rules seem broken. The twists are so extreme, they resemble a celestial ribbon caught in a hurricane. What could warp a galaxy so violently? One leading theory points to a gravitational tug of war with another galaxy, perhaps a long-forgotten collision that stretched and contorted the spiral like taffy. But here's the odd part, there's no visible culprit nearby. That's led some scientists to suspect something far more mysterious: dark matter. Invisible and pervasive, dark matter's gravitational grip could be twisting the galaxy from within, like hidden fingers kneading dough. Others speculate that NGC 262 might be harboring a supermassive black hole with an unstable orbit, its immense gravity warping the surrounding stars into this bizarre shape. Then there's the strangest possibility of all, that the twisted spiral isn't being pulled apart by outside forces, but is instead a relic of the galaxy's birth. Some simulations suggest certain galaxies could form with these chaotic spirals intact, as if the universe itself tied them into knots. If true, this would rewrite our understanding of how galaxies evolve. Every kink in those arms holds a clue, a whisper from the cosmos about forces we're only beginning to fathom, and that's what makes this object so mesmerizing. It's not just a cosmic oddity, it's a challenge, a reminder that even in the vast, ordered tapestry of the universe, there are threads we haven't learned to follow yet. The twisted spiral dares us to look deeper, to question, and perhaps even to unravel the secrets coiled within its luminous arms. Deep in the heart of NGC 262, something impossible is happening. Two supermassive black holes locked in a cosmic vault so tight they could fit between Earth and our Sun. Astronomers call them the black hole duo, and their dance is rewriting the rules of physics. These aren't just any black holes. Each weighs hundreds of millions of times more than our Sun, yet they orbit each other at a distance that would make our solar system's planets blush. Every rotation sends shockwaves through space itself, rippling the fabric of reality with gravitational waves we can detect from Earth. But here's what defies logic: black holes this size shouldn't be able to coexist so closely without colliding. Normally, their immense gravity would either slingshot one away or pull them together in a catastrophic merger. Yet these two have been circling one another for millions of years, caught in a standoff that baffles scientists. Some theories suggest they're trapped in a gravitational sweet spot, where their mutual pull is perfectly balanced by the energy of their orbit. Others think they're funneling gas and stars into a swirling maelstrom between them, creating a buffer of superheated matter that keeps them apart. The effects are staggering. Their gravitational tango stretches nearby stars into glowing streamers like taffy pulled between invisible hands. Space-time around them warps so severely that light from behind the duo bends into Einstein rings, halos of distorted starlight that act as cosmic magnifying glasses. And every few decades, their orbits tighten just enough to release a burst of gravitational waves, ripples so powerful they subtly shift the position of telescopes millions of light years away. What happens next? Simulations predict they'll eventually merge in an explosion of energy so vast it'll outshine every star in the galaxy combined, but eventually could mean another 100 million years. Until then, the black hole duo remains one of the universe's most spectacular paradoxes, a pair of cosmic titans dancing on the edge of destruction, teaching us just how little we understand about the violent hearts of galaxies. Among the swirling arms of NGC 262 lurks a cosmic ghost, the Phantom Nebula. One moment, it's a radiant cloud of glowing gas, painting the void with vibrant hues of crimson and sapphire. The next, it vanishes without a trace, as if the universe itself blinked and erased it. This isn't some trick of the telescope or a glitch in the data. Astronomers have watched it flicker in and out of existence for decades, defying every logical explanation. What could cause a nebula to disappear? One leading suspect is a variable star, a stellar vampire hidden at the nebula's heart. These unstable stars pulse in brightness, sometimes flooding surrounding gas with enough radiation to make it glow, other times dimming so drastically that the nebula fades from view. But here's the catch: no such star has ever been detected inside the Phantom. Its vanishings are too sudden, too complete, as if the gas cloud is being switched off by an unseen hand. Then there's the eerie possibility of gravitational lensing. Imagine a massive object, perhaps a rogue black hole or a cluster of dark matter, drifting between us and the nebula. Like a cosmic magnifying glass, its gravity could bend light around it, focusing the nebula's glow into detectable view at certain angles. When the lens moves, the nebula winks out. But this theory has its own problems. Lensing effects usually distort or multiply images, not erase them entirely. And then there's the most unsettling idea, that we're not seeing the nebula at all, but something else entirely. Some researchers suggest the Phantom might be a rare echo, a delayed reflection of light from a long-dead star, bouncing off dust clouds in just the right way to mimic a nebula's glow. If true, its disappearances could be gaps in the echo, like skipping stones across a pond of time. Whatever the truth, the Phantom Nebula is more than a celestial oddity. It's a riddle written in light and shadow. Each flicker is a clue, a fleeting glimpse into the hidden mechanisms of the cosmos. And until we solve it, this ghostly enigma will keep haunting the depths of NGC 262, reminding us just how much we still don't understand. Nestled within the embrace of NGC 262 lies a celestial jewelry box, the Diamond Cluster. Unlike ordinary star clusters that blaze with uniform brilliance, this one sparkles with individual stars so carbon-rich they act like cosmic prisms, bending and scattering light into dazzling displays. Imagine 1 trillion carats worth of diamonds, each one a star whose atmosphere has transformed into a glittering lattice of crystallized carbon particles. Under certain wavelengths, these stars don't just shine, they fracture light into rainbows, painting the void with fleeting flashes of emerald, sapphire, and ruby. What makes these stars so chemically peculiar? Most stars fuse hydrogen and helium, leaving heavier elements like carbon as trace byproducts. But the diamond cluster stars are cosmic overachievers. Their outer layers have become saturated with carbon dredged up from their cores, a process so rare it's only been observed in a handful of stellar oddities across the universe. Some astronomers believe these stars are dragging carbon-rich material from companion stars like cosmic vacuum cleaners. Others argue they're the product of violent collisions where carbon-heavy stellar remnants merged and reignited. Then there's the mystery of their light. Carbon molecules in their atmospheres don't just absorb light, they twist it. Similar to how a diamond's faceted structure refracts sunlight into colorful fire, these stars' carbon haze bends starlight into intricate patterns. Telescopes have caught them flickering in hypnotic rhythms, as if the cluster itself is sending coded messages across the cosmos. But the real enigma is their age. Most carbon stars are ancient, nearing the end of their lifespans, yet the diamond cluster stars burn unusually hot and bright for their composition, suggesting they're either younger than they appear or operating on physics we haven't yet deciphered. One radical theory proposes their carbon isn't stellar at all, that it's the remnants of shattered planets, their diamond cores vaporized and absorbed by the star's gravity. Whether gemstone factories or stellar cannibals, these stars challenge our understanding of cosmic chemistry. They're not just glittering decorations in NGC 262, they're laboratories, testing the limits of how stars live, die, and occasionally sparkle. Hovering silently within NGC 262 is an astronomical magnifying glass unlike any other, the gravity lens. This colossal object, likely a cluster of dark matter or a supermassive black hole, doesn't just distort light, it sculpts it. Background galaxies billions of light-years behind it appear stretched into shimmering halos called Einstein rings, their light bent around the lens like water flowing around a stone. These luminous arcs aren't just beautiful, they're cosmic shortcuts allowing us to peer farther into the universe than any human-made telescope ever could. What makes this phenomenon so extraordinary is the precision of the distortion. The gravity lens doesn't just blur distant objects, it enhances them. Like a funhouse mirror designed by physicists, it amplifies the light of galaxies so faint they'd normally be invisible, revealing details astronomers could never catch otherwise. In some cases, it even creates multiple mirrored images of the same galaxy, each one a snapshot from a slightly different angle in space-time. The real magic lies in what we've discovered through this lens. Distant star-forming regions, ancient quasars from the universe's infancy, even rogue planets drifting between galaxies, all brought into view by this natural telescope. But here's the twist, the gravity lens itself remains almost entirely invisible. Dark matter doesn't emit or reflect light, and the black hole variant swallows any radiation that could reveal its presence. We only know it's there because of the way it warps everything behind it, like spotting a hidden object by its shadow. Some researchers believe this lens might hold an even deeper secret. The pattern of distortion suggests its mass isn't evenly distributed, it's lumpy, as though smaller, unseen objects orbit within it. This has led to wild speculation. Could the lens be amplifying signals we haven't recognized yet? Brief flashes of light that don't match known cosmic events, or even whisper at structured patterns that defy natural explanation. For now, the gravity lens remains both a tool and a riddle. It gives us glimpses of the impossibly distant while hiding its own true nature, a cosmic tease both revealing and concealing the universe's deepest secrets. And every time we train our telescopes on those shimmering Einstein rings, we're not just observing distant galaxies, we're staring through a keyhole in the fabric of space itself. Drifting through the inky blackness between stars in NGC 262, two colossal wanderers trace a lonely path, the binary rogue planets. Each one a Jupiter-sized giant, they orbit one another in perfect sync, untethered to any sun. These aren't just ordinary rogue planets cast adrift by chance. They're a pair locked in a gravitational embrace as they sail through the galaxy's interstellar sea, glowing faintly with the residual heat of their violent births. Most rogue planets are solitary, ejected from their home systems by gravitational chaos. But these two defy the odds. Their synchronized dance suggests they were flung out together, likely victims of a cataclysmic encounter. Perhaps a passing star's gravity ripping them from their original orbits, or a destabilizing clash between planets in their youth. The energy of that expulsion would have been unimaginable, a cosmic slingshot powerful enough to fling two gas giants into the void without tearing them apart. Now they drift as eternal partners, their bond stronger than the forces that exiled them. What makes them visible at all is their fading infrared glow. Without a star to warm them, they've cooled over millions of years, but their immense size means they still radiate a whisper of heat. Telescopes tuned to infrared wavelengths catch this ghostly light, revealing their presence like embers in the dark. Their atmospheres likely swirl with exotic storms, perpetual tempests of frozen ammonia and methane, lit only by the dim glow of their own internal energy. But the real mystery is how they've survived. Rogue planets often freeze into barren ice worlds, their atmospheres collapsing under the relentless cold of space. Yet these two show signs of active weather, even auroras crackling along their magnetic fields. Some scientists speculate they might generate heat through tidal forces, their mutual gravity flexing their cores like cosmic stress balls. Others wonder if they're stealing material from one another, a slow exchange of gas that keeps their engines running. More unsettling is the question of what might orbit them. Rogue planets can have moons, and a binary pair could host an entire exiled solar system in miniature. Imagine frozen worlds with subsurface oceans warmed by tidal friction, or moons with atmospheres thick enough to trap heat. Could such places harbor life adrift in the darkness? It's a tantalizing thought that even in the coldest reaches of NGC 262, there might be pockets of warmth, hidden oases carried between the stars. The binary rogue planets are more than cosmic runaways. They're a testament to the violence and resilience of the universe, a reminder that even in exile there can be connection. And as they journey on, they carry with them the untold stories of how solar systems live, die, and sometimes escape. In a quiet corner of NGC 262, something screams into the void, not with light but with raw, pulsing radio waves. Astronomers call it the radio screamer, a source of bursts so rhythmic they seem almost artificial. Unlike typical pulsars that flash with predictable regularity, this object sends out signals in strange, intricate patterns, bursts that quicken, slow, and occasionally fall silent for days, as if catching its breath. The pulses aren't random noise, they're structured, layered with repeating sequences that defy the chaotic nature of most cosmic radio sources. At first glance, it might resemble a magnetar, a highly magnetic neutron star known for its energetic outbursts. But magnetars don't behave like this. Their emissions are violent and erratic, while the screamer's patterns are eerily consistent, like a cosmic metronome with a mind of its own. Some researchers suggest it could be a new class of pulsar, one with a twisted magnetic field that funnels radio waves in bizarre, unpredictable ways. Others point to the possibility of a binary system, where two dense objects like a neutron star and a white dwarf interact in a way that modulates the radio bursts like a celestial Morse code. Then there's the more speculative angle. The patterns are complex enough that some scientists have openly wondered if they're more than natural. Could these be intentional signals, a beacon from an advanced civilization? The idea isn't as far-fetched as it sounds. In the 1960s, astronomers discovered pulsars and briefly dubbed them LGM stars, short for Little Green Men. because their precise pulses seem too engineered to be natural. The Screamer's signals are even more nuanced, with fluctuations that resemble mathematical sequences rather than cosmic static. SETI researchers have analyzed them for signs of coding, though so far, no definitive evidence of artificial origin has surfaced. But here's where it gets even stranger. The Screamer isn't just emitting radio waves, it's doing so in a frequency range unusually quiet for cosmic objects. Most natural radio sources blare across a wide spectrum, but this one is oddly focused, as if tuned to a specific channel. That selectivity is rare in nature, yet inefficient for any civilization trying to broadcast widely, adding another layer to the puzzle. The truth might lie somewhere between the known and the unimaginable. Perhaps the Screamer is a cosmic oddity, a rare alignment of physics we've yet to understand. Or maybe, just maybe, it's something more, a message in the noise, waiting for the right moment to be decoded. Until then, it remains one of NGC 262's most tantalizing mysteries, a voice in the dark that refuses to be ignored. Tucked away in the outer reaches of NGC 262 lies an invisible knot of pure gravity, the dark matter knot. This dense, tangled region contains more mass than 1,000 suns, yet telescopes see nothing there but empty space. Its presence is revealed only by the way it warps the cosmos around it, bending light from distant galaxies into eerie arcs and slowing the orbits of nearby stars as if they're moving through syrup. Dark matter itself is already one of the universe's greatest mysteries, a substance that makes up 85% of all matter, but refuses to interact with light. Most of it drifts through galaxies in diffuse halos, subtly shaping their rotation. But this knot is different. It's a clump of dark matter so concentrated, it behaves like a celestial anchor, distorting space-time far more severely than typical dark matter distributions. Stars skirting its edges speed up unexpectedly, their trajectories kinked as if tugged by an invisible hand. Gas clouds split into strange, fork-like streams when they pass too close, their paths diverted by something they can't see. What could create such a dense cluster of the invisible? One theory points to the galaxy's violent past. When NGC 262 collided with another galaxy millions of years ago, the crash might have funneled dark matter into eddies and whirlpools, compressing it into these bizarre knots. Another possibility is even more unsettling, that dark matter isn't perfectly uniform, but has its own weather, with regions where it clumps like cosmic fog condensing into droplets. The knot's most startling feature is its stability. Normally, gravity would cause such a dense concentration to disperse or collapse, yet this one has persisted for eons. Some researchers speculate it might be held together by an unseen force, a property of dark matter we haven't yet discovered. Others wonder if it's not just dark matter at all, but something more exotic, a primordial black hole from the early universe, or even a wrinkle in spacetime itself, frozen in place like a knot in a tangled rope. Studying this ghostly structure could unlock secrets about dark matter's true nature. Every star it deflects, every photon it bends is a clue. And until we decipher those clues, the dark matter knot remains both a roadmap and a riddle, a shadow in the cosmos, silently reshaping the universe around it. Threading through the depths of NGC 262 like a cosmic wire stretched impossibly thin, there might exist an object so strange it bends the very rules of reality, the cosmic string. Picture a crack in the universe itself, a one-dimensional flaw in space-time left over from the Big Bang. Unlike black holes or stars, this isn't a physical object made of matter. It's a scar in the fabric of existence, a line of pure energy thinner than a proton, but with the mass of an entire mountain range packed into every inch. If confirmed, the implications would shatter textbooks. Cosmic strings are predicted by some theories of quantum gravity, but finding one would be like stumbling upon a unicorn. These relics of the early universe are thought to have formed during the intense phase transitions just after creation, when space-time itself froze unevenly, leaving behind defects like cracks in ice as it solidifies. What makes them mind-bending is their behavior. A string under tension would vibrate at nearly the speed of light, sending ripples through spacetime strong enough to briefly distort the shape of anything passing nearby. Stars might appear to flicker as their light is lensed by the string's gravity, or galaxies could show strange, straight-line distortions in their structure. The real magic lies in how we might detect one. Unlike black holes which swallow light or dark matter which cloaks itself, a cosmic string would reveal itself through subtle but unmistakable signatures. Its immense gravity could split the light of distant quasars into double images, perfectly mirrored along the string's length. Even more dramatic, if two strings crossed or a loop snapped, the event would unleash a burst of gravitational waves so powerful, it would ring across the entire observable universe like a bell. But here's the tantalizing possibility. NGC 262's unique structure might be the perfect hiding place. Some of its warped spiral arms and unexplained stellar motions could, in theory, be the result of a string's ghostly pull. A few researchers have even speculated that the galaxy's unusually straight dust lanes, regions where gas and stars align in razor-thin filaments, might trace the path of a string slicing through the cosmos like a knife. Whether real or hypothetical, the hunt for cosmic strings is more than academic. Confirming their existence would offer a direct window into the universe's first moments, proving that spacetime itself has a structure we've barely begun to map. It's the ultimate cosmic detective story, and NGC 262 might just hold the clue. At the heart of NGC 262, three blazing beacons outshine entire galaxies, the trifecta of quasars. These aren't just supermassive black holes feeding on gas and dust. They're cosmic furnaces, ejecting enough energy in a single second to power human civilization for billions of years. Each one burns brighter than 1,000 Milky Ways, their luminosity defying the known limits of black hole appetite. The sheer proximity of these three monsters is what baffles astronomers most. Normally, quasars are solitary giants separated by vast cosmic distances, but here they form a tight-knit trio, their accretion disks glowing like celestial bonfires in a cosmic campground. The first quasar, designated Q1, pulses with eerie regularity, dimming and brightening every 11 days like clockwork. This isn't random flickering, it suggests something extraordinary is happening in its accretion disk. Most quasars feed chaotically, but Q1's rhythm hints at an orderly mechanism, perhaps a massive object like a trapped star orbiting just outside the black hole's event horizon, periodically disrupting the flow of incoming matter. Imagine a celestial metronome ticking inside a hurricane, its beat somehow surviving the chaos. Q2, the middle member of the trio, presents a different puzzle. Its light spectrum shows bizarre absorption lines, gaps where certain wavelengths vanish entirely. These shadows suggest the presence of ultrafast winds, clouds of gas racing outward at nearly 1/10 the speed of light. Such winds should blow away the very material the quasar feeds on, starving it over time. Yet Q2 has burned steadily for millions of years. How? One controversial theory proposes that it's feeding on dark matter, converting the invisible substance into radiation through processes we don't yet understand. Then there's Q3, the most enigmatic of the three. Unlike its siblings, it emits almost no X-rays, an anomaly for an object this energetic. X-rays are typically produced in the hottest, most violent regions near a black hole's poles. Their absence implies something is blocking them, or worse, that our models of quasar physics are fundamentally flawed. Some researchers speculate Q3 might be surrounded by a nearly perfect sphere of fast-moving particles, a natural particle accelerator that deflects X-rays like a cosmic mirror. Together, these quasars form a laboratory for testing the extremes of astrophysics. Their proximity suggests they might be interacting, their gravitational fields warping one another's accretion disks into bizarre shapes we've never observed elsewhere. Simulations show their combined radiation could be stripping gas from nearby galaxies before it even reaches them, creating a feedback loop that sustains their incredible brightness. But the biggest question remains: how did three quasars end up so close in the first place? One possibility is that they're the remnants of a galactic merger, three supermassive black holes thrown together during a collision so violent it triggered simultaneous feeding frenzies. Another, more radical idea is that they're not separate objects at all, but a single, twisting structure. A triple quasar formed when spacetime itself folds in on itself near a black hole's event horizon, creating multiple observable images of the same object. Whatever the truth, the trifecta of quasars stands as a monument to the universe's capacity for wonder. They challenge our theories, defy our expectations, and remind us that even the brightest cosmic mysteries are still shrouded in shadow. And as we study their light, we're not just observing distant objects, we're peering into the furnace where the laws of physics are forged and rewritten. Hidden within the spiraling arms of NGC 262, there's a place where time itself stutters, the time dilation zone. Here, clocks don't tick in sync with the rest of the universe. A single minute inside this eerie region might stretch into hours outside, as if the galaxy itself has pressed pause on reality. This isn't science fiction. It's Einstein's theory of relativity playing out in one of the most extreme environments ever observed. The phenomenon stems from an invisible powerhouse at the zone's core, likely a supermassive black hole spinning at nearly the speed of light. As its immense gravity warps space-time, it creates a gradient where time slows drastically closer to the center. Astronomers first noticed the effect when tracking stars orbiting the zone's edge. Their light shifted to deeper reds, a telltale sign of time stretching under gravitational stress the closer they drifted toward the invisible epicenter. Even more bizarre, gas clouds near the zone's boundary appear frozen mid-spiral, their motion slowed to a crawl from our perspective, as if viewed through cosmic molasses. But the real proof lies in the signals. Pulsars, dead stars that emit precise radio pulses like cosmic lighthouses, show unmistakable changes when their beams pass near the zone. Their normally metronomic ticks stretch and distort, sometimes arriving seconds later than expected, as though the very fabric of space is resisting their passage. These delays match Einstein's equations with eerie precision, showing time isn't just a universal constant, it's malleable, bending under the weight of gravity like a rubber sheet. What makes this zone unique isn't just the strength of the effect, but its scale. Most time dilation occurs in extreme but localized environments, like right at a black hole's event horizon. Here, the influence spans light years, creating a vast arena where relativity becomes visible to our telescopes. Some theorize the zone might contain exotic matter or energy, amplifying the distortion. Others wonder if we're seeing the aftermath of a collision between two black holes, their merged gravity fields permanently denting space-time like a fingerprint in clay. For scientists, this region is a living laboratory. By studying how light, matter, and even time itself behave here, we're testing relativity's limits in ways no earthbound experiment could replicate. And for the dreamers among us, it's a glimpse into a universe far stranger than we imagine, and one where time, the most familiar dimension of all, becomes fluid, unpredictable, and utterly wondrous. Bursting from the core of NGC 262 like a cosmic fire hose, the antimatter fountain defies one of nature's most fundamental rules: that matter should dominate the universe. This slender jet, stretching thousands of light years into space, isn't made of ordinary particles. It's a torrent of positrons, the antimatter counterparts to electrons, colliding with stray atoms in explosive flashes of gamma-ray light. Every second, it churns out enough antimatter to power human civilization for millennia, if we could harness it without triggering annihilation on contact with our matter-filled world. What makes this fountain so baffling is its stability. Antimatter shouldn't survive long in a galaxy brimming with matter. Even in the vacuum of space, stray gas atoms should collide with the positron stream, igniting bursts of energy that would rapidly dissipate the jet. Yet here it flows, steady as a laser beam, for distances that dwarf our entire solar system. The secret may lie in its magnetic cage. Observations reveal twisted filaments of magnetic fields surrounding the jet like an invisible pipeline, channeling the antimatter away from destructive interactions. These fields are so strong, they force the positrons into a tightly focused beam, preventing them from veering off course and meeting their explosive end. The fountain's origin is even more puzzling. Most antimatter jets stem from neutron stars or black holes, where extreme physics can briefly flip matter into its opposite form. But NGC 262's central black hole shows no signs of the chaotic feeding needed to produce such a steady stream. Instead, some astronomers speculate the fountain might be fed by something far stranger, a hypothetical object called a quark star. These ultra-dense stellar remnants, made entirely of unconfined quarks, could theoretically generate antimatter through processes we've yet to observe directly. Others suggest the jet might be tapping into primordial antimatter, leftovers from the Big Bang that somehow avoided annihilation for billions of years. Then there's the light show. When the fountain's positrons finally do collide with matter, the annihilation events create gamma rays with precise energy signatures, like cosmic fingerprints proving antimatter's presence. But telescopes have spotted something odd, gaps in the expected gamma ray spectrum, as if chunks of the jet are passing through voids where matter mysteriously vanishes. One provocative theory proposes these might be antimatter bubbles, regions where the jet has carved out pockets of near-pure antimatter, floating like invisible balloons in the galactic medium. The implications are staggering. If even a fraction of this antimatter could be harvested, it would revolutionize energy production, medicine, and space travel. A single gram of antimatter contains the energy of 20,000 tons of conventional explosives. Yet the fountain also poses a cosmic riddle. Why hasn't all this antimatter annihilated with the surrounding galaxy? Is NGC 262 hiding some undiscovered mechanism that balances matter and antimatter on a razor's edge? The answer could rewrite our understanding of why the universe favors matter at all, and whether other corners of existence might harbor antimatter-dominated realms. For now, the antimatter fountain remains both a beacon and a warning. It shows us the universe's capacity for symmetry and the violence hidden within that balance. Every positron streaming from its depths carries a whisper from the dawn of time, a reminder that nature's most volatile forces often hide in plain sight. In the crowded stellar neighborhoods of NGC 262, a star died, but not like any star we've seen before. The impossible supernova didn't just explode, it refused to fade. Most supernovae blaze brilliantly for weeks before dimming into obscurity. This one burned for years, flickering with the stubborn persistence of a cosmic ember that wouldn't go out. Even stranger, its light curve, the graph astronomers used to track a supernova's brightness over time, looked nothing like the usual spikes and dips. Instead, it resembled a chaotic heartbeat, pulsing unpredictably as if the star was fighting its own demise. What makes this explosion so baffling isn't just its endurance. The spectral fingerprints of its light revealed elements that shouldn't coexist in a single event. Supernovae typically fall into two categories: type Ia, the thermonuclear detonations of white dwarfs, and type Roman II, the collapse of massive stars into neutron stars or black holes. The impossible supernova displayed characteristics of both, as though the universe had spliced two different cosmic deaths into one. Its spectra showed the telltale silicon of a type Ia alongside the hydrogen signatures of a type Roman II, a combination that defies every model of stellar physics. Then there's the radiation. Most supernovae flood space with visible light and X-rays. This one emitted erratic bursts of gamma rays and, even more puzzling, radio waves in frequencies usually associated with colliding neutron stars. Some astronomers speculate the original star might have been part of a binary system, its explosion triggering a chain reaction with a companion star or compact object. Others propose it was a pulsational pair instability, supernova, a rare beast where a star undergoes multiple explosive eruptions before its final collapse, though even that theory struggles to explain the observed energy patterns. But here's the twist: the supernova's aftermath left no visible remnant. No neutron star blink in the radio waves, no black hole's telltale X-ray glow. Just an eerie quiet where the star once blazed. The leading explanation, a failed black hole, an object so dense, its gravity traps even light, but not quite dense enough to form a proper event horizon. Think of it as a cosmic phantom, a shadow that consumes everything yet leaves no trace of itself behind. The impossible supernova challenges more than just our understanding of stellar deaths. It hints at gaps in our knowledge of how elements form, how energy propagates through space, and even what strange objects might lurk in the gray zones between known celestial phenomena. Every flicker of its lingering light is a question, one that keeps astronomers awake, staring at their screens, wondering what other impossible things the universe might be hiding. Drifting through the frozen outskirts of NGC 262, a colossal wanderer plows through space at a glacial pace, the cosmic iceberg. This city-sized behemoth isn't made of rock or metal, but of exotic ices so rare they shouldn't exist in the relative warmth of a galaxy's interior. Imagine a mountain range of frozen nitrogen, methane, and carbon monoxide, laced with crystalline compounds that form only in the deepest cold of interstellar space. Most objects this large would be shattered by stellar radiation or pulled apart by tidal forces. Yet the iceberg endures, its surface gleaming with an eerie blue hue as it reflects distant starlight. Its origin story reads like a cosmic odyssey. Born in the galaxy's outermost halo, where temperatures hover just above absolute zero, the iceberg likely spent billions of years accumulating layers of frozen gases, a snowball rolling through the void. What propelled it inward remains a mystery. Some theories suggest a close encounter with a passing star knocked it loose from its frigid cradle, while others argue it's the sole survivor of a long-vanished dwarf galaxy, a relic swallowed whole by NGC 262 during an ancient collision. What truly astonishes astronomers is its composition. Spectroscopic analysis reveals not just water ice, but layers of frozen oxygen and bizarre clathrate hydrates, cages of water molecules trapping volatile gases like cosmic champagne bubbles. These fragile structures should vaporize instantly under even weak stellar radiation, yet here they persist, protected perhaps by an outer shell of darker, more resilient organic compounds. Some researchers speculate the iceberg might even harbor probiotic molecules, the chemical precursors to life, frozen in stasis since the galaxy's youth. Then there's the anomaly at its core. Radio scans detect dense metallic reflections deep within the ice, a possible metallic hydrogen layer or something far stranger. If confirmed, it could mean the iceberg isn't just a passive chunk of frozen gas, but a layered time capsule holding secrets about how extreme cold and pressure can alter matter at cosmic scales. As it drifts closer to the galaxy's warmer inner regions, the iceberg faces its greatest threat: heat. Already, faint plumes of vapor trail behind it like a comet's tail, the first signs of its slow demise. But this destruction might be its most valuable phase. Every molecule that evaporates carries isotopic signatures from the galaxy's earliest epochs, offering astronomers a taste of pristine ingredients from a time before stars. The cosmic iceberg is more than a frozen fossil. It's a messenger from the galaxy's darkest, coldest frontiers, reminding us that even in the void, there's beauty in endurance. And as it melts, it whispers secrets of how galaxies build their worlds, one frozen fragment at a time. Nestled in the turbulent heart of NGC 262, a cosmic beast of pure force reigns supreme, the magnetic monstrosity. This sprawling region doesn't just have magnetic fields, it's a storm of invisible power with forces millions of times stronger than Earth's polar pulls. Here, magnetism isn't just a background player, it's the sculptor, the destroyer, and the architect, bending the very fabric of star formation to its will. Picture the scene. Vast tendrils of magnetized gas stretch across light years, weaving through space like the threads of a cosmic spiderweb. Stars attempting to form in this chaos don't just coalesce under gravity, they're torn apart, twisted into alignment, or crushed into premature ignition by the relentless magnetic grip. Newborn stars often erupt into life with their magnetic poles already locked into place, spinning like tops under forces that would strip a planet's atmosphere in seconds. But the real spectacle lies in how the monstrosity treats cosmic particles. Charged atoms don't drift lazily here, they're slingshotted to near light speeds, forced into spiraling paths along magnetic field lines like cars on an invisible roller coaster. When these particles collide, they don't just spark, they unleash torrents of synchrotron radiation, glowing in frequencies from radio waves to gamma rays. Telescopes pick up these emissions as eerie, looping structures, painting the sky with luminous ribbons where no physical gas or dust exists. The origin of such extreme magnetism remains hotly debated. Some theories point to the corpse of a hypermassive star, its collapsed core spinning so fast it amplified magnetic fields to absurd levels before vanishing into a black hole. Others suggest the monstrosity might be feeding on the galaxy's own dynamo effect, a self-sustaining engine where moving plasma generates ever stronger fields in a runaway cycle. Then there's the chilling possibility that we're witnessing something even more exotic, primordial magnetic threads, relics from the universe's first moments, preserved here like fossils in a cosmic amber. If true, they'd offer a direct window into conditions before the first stars flickered to life, a time when magnetism, not gravity, might have ruled the cosmos. For now, the magnetic monstrosity stands as both a marvel and a warning. It shows us how fragile the rules of star birth can be when faced with nature's hidden forces, and just how much we still have left to learn about the invisible hands shaping our universe. Amid the swirling chaos of NGC 262, an echo lingers, a whisper of light from a star that died millennia ago. The ghostly afterimage isn't a physical object but a fading fingerprint, a patch of space glowing with radiation long after its source vanished. Unlike remnants like supernova shockwaves or pulsar winds, this echo is quieter, subtler, a cosmic memory etched into the fabric of the galaxy itself. What makes it extraordinary is its persistence. Most stellar afterglows fade within decades as ejected gas disperses into the void. This one has endured for centuries, its faint ultraviolet shimmer detectable only through the most sensitive telescopes. The key lies in its composition. The star didn't just explode, it erupted in a way that ionized surrounding gas so thoroughly, the atoms are still relearning how to emit light normally. Picture a forest after a wildfire where the embers glow for years, not from fresh burning, but from the sheer intensity of the heat they absorbed. Studying the afterimage is like reading a cosmic history book. Its light spectrum carries the chemical signatures of the original star's final moments, revealing elements forged in its death throes. Iron, neon, and even traces of gold ripple through the echo, each wavelength a clue about the star's size, age, and the violence of its demise. But there's a twist. The distribution of these elements isn't uniform. Some regions show pockets of heavier atoms concentrated in strange, thread-like patterns, suggesting the star didn't just collapse, it may have been shredded by an unseen companion, its innards scattered asymmetrically like paint flung from a spinning brush. Even more intriguing is the echo's shape. Instead of a symmetrical shell, it stretches into elongated tendrils as if something, perhaps the galaxy's magnetic fields or a passing black hole's gravity, reached out and sculpted the expanding debris. This distortion lets astronomers map invisible forces at work in the interstellar medium, turning the afterimage into a natural probe for studying the galaxy's hidden dynamics. But the real mystery is the echo's energy source. Ultraviolet glows like this require constant re-energizing, yet no nearby stars or pulsars seem capable of providing the needed power. Some theorists speculate the original explosion might have left behind a magnetar with an unusually slow spin, its magnetic field still pumping energy into the remnant like a fading battery. Others propose the presence of dark matter particles annihilating at the echo's edges, an idea that, if proven, would open an entirely new window into detecting the universe's most elusive substance. The ghostly afterimage is more than a relic. It's a bridge between past and present. Every photon carries a story, not just of a star's death, but of the galaxy's ever-shifting landscape. And as it fades, it leaves behind a question: what other echoes might linger in the darkness, waiting to tell their tales? Tucked away in NGC 262's outer halo, two tiny galaxies pirouette in a slow cosmic ballet, the dancing dwarfs. These aren't just ordinary satellite galaxies, they're survivors, locked in a gravitational tug of war with their massive neighbor that's stretching them into celestial ribbons. Each pass they make around NGC 262 strips away more stars, gas, and even dark matter, leaving behind glittering trails that glow like discarded sequins across the void. The larger of the pair, nicknamed Twirl, resembles a spinning top losing its balance. Its core remains intact for now, but its outer arms have already been torn into tendrils of stars, some stretching over 20,000 light-years, long enough to wrap around the Milky Way twice. The smaller companion, Whirl, fares even worse. Once a proud, if petite, spiral, it's now reduced to a smeared smudge of light, its stars scattered into a lopsided arc resembling a half-melted snowflake. What makes this dance so mesmerizing isn't just the destruction, it's the creation. As the dwarfs orbit, their stolen stars don't simply vanish. They form shimmering bridges between the galaxies, structures astronomers call tidal streams. These rivers of starlight act as cosmic breadcrumbs, mapping the dwarfs' orbital paths over millions of years. But here's the twist: some of these streams glow far brighter than the remaining galaxies themselves, as if the act of being ripped apart has somehow ignited the stars within them. Then there's the invisible choreography, the dark matter. Though we can't see it directly, its presence is betrayed by the dwarfs' motions. They're moving faster than visible gravity alone should allow, hinting at vast halos of dark matter still clinging to them like phantom limbs. As they orbit, these halos stretch into long, faint tendrils, weaving through NGC 262's own dark matter web like roots penetrating soil, the most haunting detail. This dance is doomed. Simulations show the dwarfs have maybe another billion years before NGC 262 fully consumes them. By then, their stars will be scattered across the galaxy's halo, their dark matter absorbed into its invisible scaffold. But for now, they spin on a fleeting glimpse of how galaxies grow, not just by birthing stars but by devouring their neighbors, and in their slow-motion demise they remind us, even in the cosmos there's beauty in surrender. Floating through the star-studded waters of NGC 262, the cosmic jellyfish drifts with an eerie grace, a nebula so vast its glowing tendrils stretch across entire star systems. Unlike the static clouds of most nebulae, this one seems alive, its filaments rippling and pulsing as though stirred by invisible currents. The resemblance to its earthly namesake is uncanny, a luminous bell-shaped core with trailing arms that twist and curl like tentacles probing the darkness, each one lined with knots of newborn stars that glow like bioluminescent plankton. The secret to its mesmerizing shape lies in violence. The jellyfish wasn't born this way, it was sculpted. At its heart lies the corpse of a massive star whose death throes sent shockwaves tearing through surrounding gas, compressing some regions into stars while stretching others into these eerie, flowing strands. Radiation from those young stars now lights up the nebula from within, painting it in hues of electric blue and deep violet. But the real magic happens in the tendrils themselves. Each one acts as a cosmic nursery, with dense pockets of gas collapsing under their own gravity to form stellar embryos. Some of these protostars are so fresh, they're still cloaked in placental clouds of dust, their light barely peeking through. What baffles astronomers isn't just the jellyfish's beauty, but its defiance of physics. Nebulae this large should dissipate over time, their gas scattered by stellar winds or blown away by supernova. Yet this one persists, its structure maintained by an unseen force. Magnetic fields may play a role, their invisible lines acting like a skeleton, holding the tendrils together against the chaos of space. Or perhaps the jellyfish is feeding, siphoning fresh gas from a nearby molecular cloud, replenishing itself like a deep-sea creature drifting through fertile waters. Then there's the motion. Time-lapse observations reveal the tendrils aren't static, they sway, as if pushed by some cosmic tide. Some researchers believe this could be the fingerprint of a hidden black hole, its gravity gently tugging the nebula like a puppeteer's strings. Others argue it's evidence of dark matter flows, rivers of invisible particles carving channels through the galaxy's fabric. Whatever the cause, the effect is hauntingly beautiful. A celestial dance that's lasted millions of years with no audience but the stars themselves. The cosmic jellyfish is more than a spectacle, it's a reminder of how artistry and destruction intertwine in the universe. Every glowing filament, every newborn star tells a story of endings and beginnings written in gas and light. And as it drifts through NGC 262, it leaves behind a question. How many other wonders like this are floating unseen in the depths of space, waiting for us to look up and wonder? Deep within the spiraling arms of NGC 262, the laws of gravity don't just bend, they shatter. The gravity anomaly is a region where massive objects don't move as they should, where stars accelerate without visible cause, and where the very fabric of spacetime seems to ripple with unseen weight. Picture a stretch of space where Newton's apple wouldn't just fall. It might hover, spiral, or even shoot sideways as if tugged by invisible strings. This isn't just a glitch in cosmic mechanics, it's a full-blown rebellion against everything we think we know about how gravity works. At the anomaly's heart lies a puzzle. There's no visible source for the gravitational chaos. No black hole's shadow, no cluster of neutron stars, not even a dense knot of dark matter large enough to explain the extreme distortions. Instead, telescopes reveal what looks like ordinary space, a quiet patch of sky peppered with unremarkable stars. Yet when astronomers track those stars' movements, they veer wildly off course, their paths kinked and twisted as if navigating an obstacle course only they can see. One star, observed over a decade, suddenly doubled its speed for no apparent reason, then just as abruptly slowed down like a car hitting an unseen speed bump in the void. The leading theory involves something called hidden mass, a concentration of matter so dense it warps spacetime like a bowling ball on a trampoline, yet emits no light. But here's where things get strange. Even if this mass were made entirely of dark matter, current models can't account for the anomaly's localized intensity. It's as if gravity itself is being amplified in this one region, like a cosmic magnifying glass focusing not light but sheer gravitational pull. Some researchers speculate the answer might lie in extra dimensions, a wrinkle in higher dimensional space that leaks additional gravitational force into our universe. Others propose a radical idea that the anomaly is a gravitational echo, a remnant of a long-vanished black hole whose gravitational waves froze in place, imprinting a phantom weight on the fabric of reality. Then there's the eerie side effect, time dilation without a cause. Clocks aboard probes passing near the anomaly in simulations at least tick noticeably slower than those farther away, as if the region was steeped in an invisible gravitational well. Yet there's no curvature of spacetime deep enough to explain the effect, just the faintest shimmer in the cosmic background radiation, a whisper of heat left over from the Big Bang that seems to skirt around the anomaly's edges like water flowing around a rock. The gravity anomaly isn't just a scientific curiosity, it's a crack in the foundation of physics. Every odd movement, every unexplained ripple, is a clue that our understanding of the universe's most fundamental force might be incomplete. And until we solve its riddles, this rogue patch of space will keep defying the rules, reminding us that even gravity, the force that binds the cosmos, still holds secrets we've yet to unravel. In the bustling stellar metropolis of NGC 262, where stars jostle for space like city lights seen from above, there's a place where the sky goes dark, the starless void. This gaping hole in the galaxy's fabric isn't just a sparse patch. It's a near-perfect sphere of nothingness, stretching over 300 light-years without a single star, nebula, or even a wisp of interstellar dust to break the emptiness. It's as if some cosmic hand reached in and scooped out a chunk of the universe, leaving behind a void so pristine, it defies every law of galactic ecology. At first glance, the void seems like it could be the aftermath of a catastrophe, a chain reaction of supernovas so violent they blew away all nearby matter like clearing a table with a hurricane. But supernova remnants leave clues, shockwaves, heated gas, the chemical fingerprints of heavy elements. This void is eerily clean, with no trace of the turbulent aftermath you'd expect from such an explosion. Even stranger, its edges are razor-sharp, as if cut with intention rather than torn by chaos. That precision has led to wilder theories. Could this be the work of a Kardashev Type 3 civilization, harnessing the galaxy's energy to construct something unimaginable? Theoretically, an advanced society might clear space to build a Dyson swarm, a vast array of energy collectors encircling a star. But a Dyson swarm requires a star to begin with, and this void has none. Unless, of course, those stars were dismantled entirely, their matter repurposed into structures we can't yet detect. It's a tantalizing thought, though skeptics point out that nature rarely needs aliens to explain its oddities. Then there's the dark matter angle. Some models suggest certain configurations of dark matter could create gravitational shadows, regions where normal matter is repelled rather than attracted. If such a knot of exotic matter lurks in the void, it might act like an invisible bouncer, keeping stars and gas out while remaining undetectable to our telescopes. But the most haunting possibility, the void might not be empty at all. It could be filled with primordial black holes, ancient, city-sized relics from the Big Bang, too small to detect directly but numerous enough to collectively carve out this pocket of nothingness. Their combined gravity would act like a cosmic vacuum, silently hoarding any matter that drifts too close. The starless void is more than an absence, it's a mirror held up to our ignorance. Every theory we throw at it reflects back unanswered questions. Whether sculpted by catastrophe, intelligence, or physics we've yet to discover, this blank spot in the galaxy challenges us to admit how much we still don't understand, and how many wonders might hide in plain sight, disguised as nothing at all. Amid the swirling gas and dust of NGC 262, a celestial prism drifts silently the crystal cloud. This radiant nebula doesn't just glow with the soft luminescence of starlight. It sparkles, fracturing light into dazzling rainbows as if space itself has been studded with microscopic diamonds. The secret lies in its composition, trillions of tiny silicate crystals, each no larger than a grain of pollen, suspended in the nebula's frigid embrace. These aren't the chaotic dust motes found in most nebulae, but perfectly aligned lattices. Their geometric structures so precise they act like natural diffraction gratings, bending starlight into spectral displays that would put earthly gemstones to shame. How could such delicate structures form in the harshness of space? The answer lies in an exotic dance of temperature and chemistry. Most nebula dust condenses in the searing heat near stars, forming irregular, jagged grains. But the crystal cloud resides in one of the galaxy's coolest regions, where temperatures hover just a few degrees above absolute zero. In this deep freeze, atoms move slowly enough to arrange themselves into orderly crystalline patterns, like frost-forming intricate patterns on a windowpane. Add to this a whisper of ultraviolet light from distant stars, just enough to nudge molecules into position without shattering their delicate bonds, and you've got a recipe for cosmic jewelry on an unimaginable scale. The real magic happens when starlight hits these crystals. Unlike ordinary dust that merely scatters light, the cloud's crystalline matrix splits it into vivid color bands, creating iridescent halos around every star that backlights it. Astronomers have catalogued hues here that don't exist in typical nebulae: shimmering violets, electric blues, and even a near-mythical forbidden red. A wavelength so rare in nature it was once thought impossible to produce outside of laboratories. Some sections of the cloud even exhibit birefringence, a property where light splits into two polarized beams, making background stars appear as ghostly doubles when viewed through certain filters. Yet the crystal cloud isn't just a pretty anomaly, it's a time capsule. The specific types of crystals found here, enstatite and forsterite, rich in magnesium, are identical to those discovered in ancient meteorites that fell to Earth. That suggests this nebula might preserve conditions similar to those in our own solar system's infancy, when similar crystals seeded the raw materials for planets. If that's true, studying this glittering cloud could reveal how stardust transforms into the building blocks of worlds, but there's a looming tragedy. The cloud's perfection is fragile. As NGC 262's spiral arms churn, the nebula drifts closer to regions of intense radiation. Already, the outermost crystals show signs of damage, their lattices warping under stellar winds, their rainbows dimming. Within a few million years, this cosmic prism could fade into a mundane dust cloud, its crystalline magic lost forever. That impermanence makes it all the more precious, a fleeting masterpiece written in light and geometry, reminding us that even in the vastness of space, beauty can be as delicate as it is dazzling. Some stars are born to wander, but few travel as fast or as far as the hypervelocity runaway. This blazing outcast isn't just drifting through NGC 262, it's tearing across the galaxy at over 2 million miles per hour, fast enough to cross the distance from Earth to the Moon in less than 7 minutes. At that speed, gravity itself struggles to keep up, and the star's trajectory paints a clear message across the cosmos. It's not just moving, it's escaping. The runaway story likely began in chaos. Most hypervelocity stars get their kick from a close encounter with a supermassive black hole, and NGC 262's central monster fits the bill perfectly. Picture this: once the star orbited peacefully in a binary pair, circling another star in the crowded heart of the galaxy, but then disaster struck. Drifting too close to the black hole's grasp, the binary system was ripped apart. One star captured, the other flung outward like a slingshot's projectile. The energy of that gravitational interaction was so immense, it didn't just nudge the runaway, it launched it like a cosmic cannonball, accelerating it to speeds that defy comprehension. Now the star barrels through the galaxy's outskirts, a solo traveler on a one-way trip into intergalactic space. Spectroscopic analysis reveals its composition: a blue-white giant, its outer layers scorched by the violence of its expulsion. Iron, silicon, and neon streak through its spectral signature, elements forged in the crucible of stellar cores and now carried like luggage on this endless journey. But the real shock: the runaway isn't slowing down. Most stars ejected at these speeds would gradually decelerate, tugged by the collective gravity of the galaxy's stars and dark matter. Yet this one shows no signs of stopping, its velocity so extreme it's effectively unshackled from NGC 262's gravitational bonds forever. Then there's the trail it leaves behind, not of stardust but of disrupted motion. As the runaway plows through interstellar gas, it creates a bow shock, a glowing ripple in the galactic medium like the wake of a speedboat. This turbulence lights up normally invisible hydrogen clouds, marking the star's path with ghostly, ephemeral flares. Some astronomers jokingly call it cosmic breadcrumbs, though these clues lead not home but to the void beyond. What awaits the hypervelocity runaway? In a few million years, it'll breach the galaxy's outer halo, becoming a true interstellar nomad. From there, it could drift for billions of years, a lonely beacon in the darkness between galaxies, its light fading as nuclear fuel dwindles. Or more intriguingly, it might one day collide with another galaxy, a splash of foreign starlight in an alien sky. For now, though, it serves as a reminder of the black hole's power and the universe's capacity for flinging its children into the unknown. The runaway carries with it the story of its birth, its violent ejection, and its defiant escape. And as it speeds toward the abyss, it leaves behind a question: how many other stars have met similar fates, hurled into the night by forces beyond their control? Deep in the tangled heart of NGC 262, reality itself flickers welcome to the quantum fluctuation. This region doesn't play by the rules. Here, particles wink into existence without warning, linger for fractions of a second, then vanish as if the universe itself can't decide whether they should be real. It's quantum mechanics writ large, not in some controlled lab experiment, but across light years of space, where the fabric of existence seems to stutter like a malfunctioning projector. The effect is subtle at first glance, just faint, sporadic flashes in otherwise empty space. But look closer and the pattern emerges. Telescopes tuned to high-energy wavelengths catch these fleeting bursts, gamma-ray sparks, sudden X-ray pops, even radio pulses that last no longer than a human heartbeat. What's bizarre is their distribution. Unlike cosmic rays or pulsar emissions, these flashes aren't coming from any detectable source. They're not the death throes of stars or the screams of black holes. They're just there, and then they're not. This isn't just random noise. The fluctuation follows a peculiar rhythm, with activity spiking in cycles that match no known celestial timetable. Some theorists suggest we're witnessing vacuum decay, a phenomenon where empty space briefly boils, spawning particle-antiparticle pairs that annihilate almost instantly. Normally, this happens on scales too tiny to observe, but in NGC 262 something, perhaps a hidden concentration of dark energy or an exotic gravitational field, is amplifying the effect to cosmic proportions. Then there's the entanglement angle. A handful of the detected particles seem linked, their properties correlated across distances that defy classical physics. When one flashes at the fluctuation's eastern edge, its partner might blink into being light years to the west, mirroring its quantum state instantaneously. This spooky action at a distance, as Einstein called it, usually happens between particles carefully prepared in labs. Out here, it's happening naturally, on a scale that could rewrite our understanding of quantum fields in deep space. The most unsettling possibility: the fluctuation might not be entirely natural. Some models propose it's the fingerprint of a technology, a quantum communication network built by an advanced civilization, using entangled particles to transmit information faster than light. Others argue it's more likely a cosmic accident, a rare alignment of physics where the galaxy's magnetic fields and dark matter distribution conspire to magnify quantum weirdness to observable levels. Whatever the cause, one thing is clear: the quantum fluctuation is a window into the universe's most fundamental layer. Every flicker, every ghostly particle, is a reminder that reality as we know it might just be the tip of the iceberg, and beneath the surface, the cosmos is far stranger than we ever imagined. Imagine a storm so vast it could swallow our entire solar system, not for days or years, but for millennia. The eternal storm isn't just a tempest, it's a maelstrom of seething plasma, a vortex of charged particles raging across NGC 262 with the fury of 1,000 suns. If Jupiter's great red spot is a hurricane, this is that storm's cosmic big brother. an atmospheric beast scaled up to galactic proportions, where the winds don't blow with mere supersonic speed, but at a significant fraction of light speed. What keeps this monster alive? Unlike planetary storms, which feed on temperature differences and rotation, the eternal storm draws energy from something far more exotic, the galaxy's own magnetic heartbeat. Twisted magnetic fields woven through the plasma like invisible wires trap and accelerate particles into a self-sustaining loop. Electrons spiral along these fields, emitting synchrotron radiation, an eerie glow that paints the storm in hues of violet and gold, visible even across interstellar distances. The result is a structure that refuses to dissipate, a whirlpool of energy locked in an endless dance. But here's the twist: the storm isn't static. Time-lapse observations reveal tendrils of plasma stretching and snapping like whips, creating shockwaves that ripple through the surrounding gas. These aren't just random fluctuations, they follow fractal patterns, repeating on scales from light years down to mere thousands of kilometers. It's as if the storm is alive, constantly reorganizing itself to preserve its colossal form. Some researchers compare it to a living organism, a self-regulating system where turbulence begets order and chaos sustains stability, the storm's most baffling feature. Its sound, converted into frequencies audible to human ears through clever data sonification, the eternal storm's electromagnetic emissions produce a deep, pulsing roar, not the erratic crackle of lightning, but a rhythmic, almost melodic thrum. This song shifts pitch over decades, suggesting the storm isn't just mindless chaos, but a dynamic structure with its own internal logic. Could this be the galaxy's way of tuning its magnetic fields, like a cosmic violin string vibrating in the dark? Yet for all its violence, the storm serves a purpose. Its relentless churning acts as a particle accelerator, forging heavy elements and flinging them far into the galaxy. Without such cosmic cauldrons, the universe might lack the diversity of atoms needed to build planets or life. So while the eternal storm seems like a force of destruction, it's also a hidden architect shaping the raw materials of existence itself. And that's the paradox at its heart, a phenomenon born from chaos governed by laws we're still deciphering, yet indispensable to the galaxy's story. The storm doesn't just rage, it matters, and as we watch its luminous tendrils pulse across the void, we're reminded that even the universe's most violent creations can be, in their own way, beautiful. Among the countless enigmas of NGC 262, none twist the mind quite like the twin paradoxes, two celestial objects locked in a cosmic contradiction. These identical stellar remnants, born from the same collapsing star, should mirror each other in every way, yet one burns bright and youthful while its sibling languishes, aging at a fraction of its twin's pace. It's as if time itself has fractured, splitting reality into parallel streams where the laws of physics no longer sync. The first twin, dubbed Chronos, behaves as expected, a pulsar spinning at a steady rhythm, its surface seething with the heat of newborn neutron star material. Its pulses arrive like clockwork, each radio beacon marking another predictable step in its life cycle. But its counterpart, Kairos, is a ghostly echo of what it should be. Though forged from the same supernova, its spin is sluggish, its surface temperature eerily cool, as though decades have passed for Chronos while mere months slipped by for Kairos. The disparity isn't just puzzling, it's impossible under known physics. Twin neutron stars from the same collapse should age in lockstep, their fates entwined by identical origins. The leading theory points to gravity's grip. Perhaps Kairos orbits something unseen, a black hole or dark matter knot whose immense gravity stretches time around it, slowing local clocks relative to the wider galaxy. Einstein predicted this effect, but never on such a dramatic scale. For Kairos to lag this severely, it would need to skirt an object so dense it warps space-time like a whirlpool in a cosmic river. Yet telescopes find no such monster nearby, leaving astronomers to wonder if Kairos is instead caught in a rare space-time kink, a wrinkle left over from the birth of the universe where time flows differently. Then there's the quantum angle. Some models suggest Kairos might be entangled with its twin not just by birth, but by quantum links that transcend distance. In this scenario, interactions with exotic particles or fields could be leaching energy from Kairos, effectively putting its internal clocks in slow motion while the rest of the universe marches on. It's a fringe idea, but the mere possibility sends theorists scrambling to rewrite equations. But the real enigma lies in the twin's light. Kronos pulses with crisp, clean radio waves, while Kairos' signals are smeared as if broadcast through a fog of time. Analysis reveals something even stranger. Kairos' light spectra show subtle shifts in elemental signatures, hinting that nuclear decay, a process thought to be immutable, might be progressing slower within its core. If true, this challenges not just astrophysics but the bedrock of particle science. The twin paradoxes are more than celestial oddities. They're a living experiment in the nature of time itself. Every pulse from Kronos, every lagging whisper from Kairos, forces us to confront the unnerving truth. That time, the most constant-seeming force in our lives, might be far more malleable than we ever dreamed. And somewhere in their dissonant beats lies a secret one that could unravel the fabric of reality or weave it anew. Behind the mind-bending wonders of NGC 262 lies an equally astonishing truth. None of these discoveries would be possible without the revolutionary telescopes that brought them into focus. The galaxy's secrets didn't surrender easily. It took cutting-edge instruments, each pushing the boundaries of technology to peel back the layers of cosmic mystery. Take the colossal radio arrays first, networks of dishes spanning continents, working in unison to catch whispers from the void. These aren't your grandfather's telescopes. By combining signals from antennas thousands of miles apart, they mimic a single dish the size of Earth itself, achieving resolution so sharp they could spot a coin on the lunar surface. It's this staggering precision that revealed the radio screamer's rhythmic pulses and mapped the tangled magnetic fields of the eternal storm. But radio waves only tell part of the story. Enter the space-based titans like the Hubble and James Webb telescopes, orbiting above Earth's blurring atmosphere to capture crystal-clear visions of the unseen. Hubble's ultraviolet eyes pierce through dust clouds to spy the ghostly afterimage's fading glow, while Webb's infrared gaze uncovered the diamond cluster's crystalline sparkle, seeing heat signatures invisible to other instruments. These observatories act as cosmic time machines. Webb, in particular, can detect light from the universe's first galaxies, yet it's also unraveling the chemistry of NGC 262's most exotic objects like the antimatter fountain's positron jet. Then there are the specialized hunters. The Chandra X-ray Observatory, for instance, specializes in high-energy emissions, revealing the scorching temperatures around the trifecta of quasars and the black hole duo's gravitational clashes. Meanwhile, ground-based spectrographs dissect starlight into rainbow-like spectra, exposing the elemental fingerprints hidden within the hypervelocity runaway's glow or the quantum fluctuations particle burst. But perhaps the most groundbreaking tools are the ones we don't see at all. Gravitational wave detectors like LIGO and Virgo sense ripples in spacetime itself, offering an entirely new way to study cosmic events. While they haven't yet pinpointed a signal from NGC 262's dancing dwarfs or the gravity anomaly, their future upgrades could turn these theoretical murmurs into observable data. Similarly, neutrino observatories buried deep underground or under Antarctic ice silently track ghostly particles from the galaxy's most violent processes, like the impossible supernova's lingering fury. What ties these instruments together isn't just their technological prowess, it's their teamwork. No single telescope can decode NGC 262 alone. Radio arrays pinpoint strange signals, optical telescopes image their sources, spectrographs decode their chemistry, and X-ray probes uncover their violent energies. It's a symphony of observation, each instrument playing a unique part in the orchestra of discovery. Yet for all their power, these tools are only as good as the questions we ask. Every leap in telescope technology has rewritten NGC 262's story, revealing objects we didn't know to look for, like the crystal cloud's prismatic dust or the time dilation zone's relativistic slowdown. And with next-generation telescopes on the horizon, like the extremely large telescope and the square-kilometer array, one thing's certain: the galaxy's strangest chapters are still being written. So the next time you marvel at these cosmic oddities, remember, they're not just wonders of nature, they're triumphs of human curiosity, each one a testament to our relentless drive to build lenses powerful enough to interrogate the universe itself. And as our tools evolve, so too will the mysteries they unveil, ensuring NGC 262 never runs out of surprises. For all the mind-bending wonders we've explored in NGC 262, the most thrilling part remains what we still don't understand. These celestial oddities aren't just cosmic decorations, they're glaring exceptions to our astrophysical rulebooks, each one exposing gaps in our knowledge big enough to sail a galaxy through. Take the twisted spiral's unnatural warping. We can model galaxy formation backward and forward, but nothing explains how its arms could contort so severely without visible outside influence. Is there a hidden force at play, some property of dark matter we've yet to account for? Or worse, could this be evidence that our fundamental understanding of galactic dynamics is incomplete? Then there's the Phantom Nebula's disappearing act. Nebulae don't just vanish, they diffuse, they dissipate, they get blown apart by stellar winds. Yet this one winks out like a switched-off lamp, leaving no trace. Current physics offers no mechanism for such clean, total disappearance. The leading theories sound more like science fiction. Hidden dimensional folds temporarily swallowing the nebula, or some unknown quantum effect causing its particles to decohere en masse. Every time astronomers think they've pinned down an explanation, the phantom defies them again, laughing in the face of conventional astrophysics. Perhaps most unsettling are the twin paradox neutron stars. Einstein's relativity allows for time dilation, but never before have we observed two objects from the same supernova aging at radically different rates. Kairos's sluggish decay suggests time itself might flow differently in its vicinity, but scans show no massive object nearby that could warp spacetime so severely. This forces us to confront uncomfortable possibilities. Could there be exotic matter creating localized time fields? Or might certain quantum states affect the passage of time on macroscopic scales? The twins don't just challenge astrophysics, they poke at the bedrock of reality itself. Even the seemingly straightforward objects here hide layers of mystery. The hypervelocity runaway moves too fast. Its speed exceeds all plausible black hole slingshot models. The antimatter fountain produces too much antimatter too steadily, violating our estimates of how much should naturally exist. And the gravity anomaly, its distortions match no known distribution of dark matter, hinting at either unseen structures or, more radically, that gravity itself might behave differently under certain extreme conditions we've yet to replicate or understand. These aren't just gaps in knowledge, they're chasms. Each anomaly represents a potential revolution in physics, waiting for the right mind to bridge the divide between observation and theory. They force us to question whether we're seeing flaws in our models or glimpses of something far grander, an entirely new layer of cosmic mechanics lurking just beyond our current mathematics. Maybe dark matter interacts in ways we've never imagined. Maybe spacetime has textures we've yet to map. Or perhaps, like early astronomers puzzling over quasars before understanding black holes, we're staring at something that will one day seem obvious once we develop the tools and concepts to see it clearly. That's the exhilarating promise of NGC 262. Its strangest objects aren't roadblocks to understanding, their signposts pointing toward discoveries we can't yet name. Every inexplicable flicker, every paradoxical orbit is the universe whispering, "Look closer, think deeper, imagine wilder." The answers won't come easily, but the questions themselves are gifts, invitations to venture beyond the edges of our cosmic maps into territories where new physics awaits. The mysteries of NGC 262 won't stay unresolved forever. Powerful new tools are already being built to pry open its secrets. Leading the charge is the upcoming Nancy Grace Roman Space Telescope, set to launch within the decade. With a field of view 100 times wider than Hubble's, Roman will map the galaxy's warped structures like the twisted spiral in unprecedented detail, potentially revealing hidden dark matter filaments or gravitational anomalies that could explain their distortions. Even more exciting, its coronagraph instrument, designed to block starlight, might finally image rogue planets like the binary rogue duo directly, transforming them from infrared blips into tangible worlds with observable weather patterns. On the ground, the extremely large telescope ELT will soon peer into NGC 262 with a mirror so vast, nearly 40 meters across, it could spot a car's headlights on the moon. The ELT's adaptive optics will cut through atmospheric blur to study the time dilation zone in real time, tracking individual stars as their orbits slow near the anomaly. Its spectrographs will dissect the light from the Phantom Nebula during its vanishings, hunting for chemical traces that could betray its true nature. And if the twin paradox neutron stars have any hidden companions, the ELT's resolution could expose them, settling the debate over Kairos' sluggish aging once and for all. But hardware alone isn't enough. Artificial intelligence is revolutionizing how we process cosmic data. Machine learning algorithms now sift through petabytes of telescope observations, flagging oddities humans might miss, like the radio screamer's patterned bursts or subtle flickers in the quantum fluctuation. Projects like the Vera-C, Rubin Observatory's legacy survey of space and time, will leverage AI to monitor NGC 262 continuously, creating the first real-time movie of a galaxy's evolution. These tools might catch the exact moment the antimatter fountain's jet flickers, or spot a previously unnoticed object warping the gravity anomaly's surroundings. Then there's the dark horse, gravitational wave astronomy. Future detectors like LISA, a space-based observatory sensitive to low-frequency ripples in spacetime, could sense collisions between intermediate black holes hidden in NGC 262, events too subtle for current instruments. If the black hole duo's dance sends out gravitational waves at frequencies LISA can detect, we might witness their spiraling death throes in exquisite detail. Similarly, pulsar timing arrays, networks of precisely monitored neutron stars, could use the galaxy's millisecond pulsars as natural gravitational wave sensors, turning the entire region into a cosmic listening post. Perhaps most promising are the wildcard technologies still in development. Plasma physics experiments mimicking the eternal storm's conditions could unlock how magnetic fields sustain such colossal structures. Quantum computers might simulate the crystal cloud's molecular lattices atom by atom, revealing how delicate crystals survive in deep space, and proposals for interstellar probes, though decades away, raise the tantalizing possibility of sending nano-spacecraft to fly through the starless void, sampling its emptiness for hidden particles or fields. The key to these breakthroughs lies in collaboration. No single tool can crack NGC 262's puzzles alone. It'll take telescopes across the electromagnetic spectrum, AI brains parsing data, and theorists refining models in response. Each anomaly we've explored demands its own specialized approach, yet they're all pieces of the same grand cosmic puzzle. And as these technologies come online, they won't just answer old questions. They'll uncover new enigmas we can't yet imagine, ensuring NGC 262 remains a frontier of discovery for generations to come. What's certain is this: the galaxy's strangest objects have spent eons hiding in plain sight. Soon, they'll have nowhere left to hide. Finding NGC 262 in the night sky might seem daunting at first. After all, this distant galaxy sits over 200 million light-years away. But with the right tools and a little cosmic guidance, you can spot its faint glow from your own backyard. Let's start with the simplest method: astronomy apps. Programs like Stellarium or Sky Safari transform your phone into a portable planetarium. Open the app, search for NGC 262, and it'll pinpoint the galaxy's location in real time, adjusting for your exact coordinates and the time of night. Look for it nestled between the constellations Andromeda and Cassiopeia, a region rich with star clusters and nebulae that can serve as celestial landmarks. For those who prefer a more hands-on approach, grab a star chart and locate the Great Square of Pegasus first. This bright asterism acts as a launching pad. From there, trace a line toward the glittering W shape of Cassiopeia. NGC 262 lies just southwest of the star Mirage, a reddish beacon in Andromeda that's visible even under light-polluted skies. At magnitude 13, the galaxy won't leap out like Andromeda's famous M31, but with a 6-inch or larger telescope under dark skies, you'll catch its faint, elongated smudge. Patience is key. Let your eyes adjust and use averted vision, glancing slightly to the side of the target to engage your retina's more light-sensitive rods. If you're hunting with a computerized go-to telescope, the process becomes even more thrilling. Enter NGC 262's coordinates, and your scope will slew directly to it, though you might still need to fine-tune the focus. Experienced observers recommend using an oxygen 3 filter to enhance contrast, as it dims light pollution while highlighting the galaxy's ionized gas regions. For astrophotographers, stacking multiple long exposure shots can tease out details invisible to the naked eye, perhaps even hints of the twisted spirals, warped arms, or the faint glow of the diamond cluster. No matter your method, remember this: every photon hitting your eyeball or camera sensor has traveled since the age of dinosaurs to reach you. That faint smudge isn't just another deep sky object, it's a gateway to 30 cosmic mysteries, waiting for you to explore them from your own corner of the cosmos. NGC 262 isn't just a gallery of cosmic oddities, it's a mirror held up to the universe, reflecting how little we truly grasp. Every twisted spiral, every flickering nebula, every rogue planet drifting untethered forces us to confront a humbling truth. The rules we've written for how galaxies behave, how stars live and die, even how time itself flows, might only apply to our tiny corner of existence. This single galaxy, with its 30 enigmas, dismantles assumptions like a whirlwind scattering pages from a textbook. If phenomena like the twin paradox or the quantum fluctuation can exist here, what other impossibilities might lurk in the trillion other galaxies we've yet to study? Consider the scale of our ignorance. A century ago, we didn't know galaxies existed beyond the Milky Way. Today, we're stumbling over objects that defy categorization, like the antimatter fountain, a structure that by all rights shouldn't persist, yet does. Or the time dilation zone, where relativity isn't just a theory but a visible, measurable spectacle. These aren't mere curiosities, they're signposts pointing toward entire branches of physics we've yet to imagine. If dark matter can knot itself into invisible tangles that warp entire galaxies, what other unseen forces might be sculpting the cosmos? If a nebula can vanish and reappear like the Phantom, what does that say about the stability of reality itself? Yet amidst the mystery lies an exhilarating promise. NGC 262 proves the universe is far stranger, far more creative than our boldest science fiction. Every anomaly we uncover isn't just a gap in knowledge, it's an invitation. An invitation to rethink gravity, to question how matter organizes itself, to wonder if life might thrive in places we've never thought to look. Could the crystal clouds' pristine lattices seed planets with chemical building blocks we've never encountered? Might the magnetic monstrosities' furious energies birth stars in ways that rewrite the life cycle of galaxies? The answers could redefine not just astronomy, but our very place in the cosmos. This is the gift of NGC 262. It reminds us that discovery isn't about filling in the blanks of existing theories, but about finding the blanks we didn't know were there. For every puzzle solved like the black hole duo's dance, explained by delicate gravitational balances, a dozen new questions erupt. And that's the heart of science, not certainty, but wonder. Wonder that propels us to build bigger telescopes, to simulate deeper quantum fields, to keep looking up and asking, what else? So when you gaze at the night sky, remember, the twinkling lights aren't just stars. They're fragments of a universe that's wilder, messier, and more astonishing than we've dared to dream. And if one galaxy can hold 30 mysteries, imagine what wonders still hide in the dark, waiting for the curious to shine a light. From the warped spirals of the twisted spiral to the haunting vanishings of the Phantom Nebula, NGC 262 has shown us a universe far stranger than fiction. These 30 cosmic oddities aren't just quirks, they're glaring reminders of how much we still don't understand. Take the black hole duo locked in a gravitational dance that defies physics, or the time dilation zone where clocks tick at different speeds for no discernible reason. Even seemingly simple objects like the cosmic iceberg, a frozen relic drifting toward destruction, challenge our assumptions about how galaxies evolve. What makes these mysteries so thrilling isn't just their strangeness, it's their defiance. The antimatter fountain shouldn't exist, yet it streams positrons into space with eerie stability. The quantum fluctuation laughs at our notions of reality, flickering particles into existence like a cosmic light switch, and the twin paradox neutron stars. They're not just celestial oddities, they're a direct challenge to Einstein's relativity, proving time itself might be more malleable than we ever imagined. Each object whispers the same truth: our rulebooks for the universe are still being written. This galaxy is more than a collection of anomalies, it's a classroom. The magnetic monstrosity teaches us how invisible forces sculpt star birth, while the ghostly afterimage shows how stellar deaths echo across millennia. The hypervelocity runaway is a lesson in galactic violence, and the dancing dwarfs reveal how galaxies grow by devouring their neighbors. Even the starless void, that eerie blank spot in the cosmos, reminds us that absence can be as revealing as presence. Every mystery here isn't just a gap in knowledge, it's an invitation to explore further, think deeper, and question braver. And that's the real gift of NGC 262. It doesn't just show us what we don't know, it hints at discoveries waiting just beyond our grasp. Could the crystal cloud's prismatic dust hold secrets about planet formation? Might the radio screamer's patterned bursts be more than natural phenomena? The answers lie in the next generation of telescopes, the next bold theories, the next curious minds willing to stare into the unknown and ask, what if? So keep looking up. The universe is far stranger, far more wondrous than we've yet imagined. And if one galaxy can hold 30 mysteries, imagine what else is out there waiting to be discovered. For more cosmic wonders and mind-bending explorations, hit subscribe, because the greatest discoveries are still ahead and we're just getting